All right, so we're doing this one, ED204. And so I've got my Debian Linux machine running here on an Intel processor. And so I've already installed the necessary software here. And I've already installed Metasploit. So here you get the necessary code to build software and to run 32-bit software on a 64-bit machine, GDB to debug it, and curl to download things from the web. Here you install Metasploit, which we're going to use to make some malware. And now we're going to download and run the vulnerable program. So we're going to have the C code for it here. This will fetch it from my server. And let me make this a little bit wider and make that prettier. All right. And now I'm going to get the executable code, which is the same thing without the .c. And now I'm going to make it executable for chmod plus x. All right. And now I should be able to run it. And it's going to tell me I have to give it a string as a command line argument. So if I give it hi, it echoes back hi. All right. So now I can check the source code. Let's do a cat of that. All right, and the source code is pretty short. It includes a few libraries, and then here it's going to have a buffer with room for 1,024 characters. It's taking a command line argument, and if there's no command line argument, so the number of argument counters on the line is not equal to 2, then it will print that message. Otherwise, it will do a string copy of the argument into that buffer and print the buffer and print a carriage return and then exit. So it's just an echo program that echoes back whatever you put in, but it copies it into a buffer with room for 1,024 characters first. So there is a possibility of overriding it with a buffer overflow, but that's not what we're going to do. What we're going to do is we're going to exploit this command that prints it with no format string. Now remember, the correct way to do print statements in C is this way. You print, you have a format string that has specifiers to tell it where you're going to print the variables, then you put the variable. So it's going to take this variable and it's going to put it here and interpret it as a string. But you can just print a variable without a format string. And if you just print the variable there, it'll make some default format so you can see the value, but it's sort of ugly looking. But what you could also put a format string in this buffer if it's under your control. And here it is. This buffer came from the command line argument. So this is the vulnerability. This is called a print format string vulnerability. So it comes, so if I run this thing, I already did this part. If I run it and I give it like hello, it just echoes hello. But if I run it and I give it a format string like %x, then it's going to execute this command that says print %x, and it doesn't have any variable. Now here you have to understand what this looks like in assembly code. In assembly code, calling a function is a several step process. First you push the parameters on the stack, the arguments, then you call the function. So it's going to take the format string here and put it on the stack, and it's going to call the function. The function is going to look for the first data it finds on the stack, and that's the format string, and it's going to take whatever data it finds after that and assume that is the variable I'm supposed to be printing. Because C has sort of amnesia, each command forgets what the previous commands were, it doesn't know that the user did not in fact give it the name of a variable to print. It just prints whatever it finds on the stack, so I get some random value here. So this is a information disclosure vulnerability. I can now see something which the developer did not intend for me to see. In fact, I can see a lot of them. I can just keep doing %x here, and I'll get a whole bunch of bytes off the stack containing data. So that's pretty interesting. Now, I can also give it a different format string. Like, you know, I could give it %d, and that would interpret this stuff as decimals instead of hexadecimal pointer type values, and then it'll give them to me in decimal. But the strangest thing to do is use %n. If I use %n and give it, say, 4 of them, I'll get a segmentation fault, and that's because the %n format string in C is very bizarre. It writes to that location in memory instead of reading from that location in memory. So now I'm writing to locations in memory, these locations here, specified by random data, and of course I don't have to try too many times before it's going to find something that's not valid address there, that's not part of the address range reserved for this program to use, so it's going to crash. So that means I can now write to memory. Because of the way the programmer wrote this, when they forgot to put a format string in this command, they gave me the ability to write to arbitrary locations in memory. If I can find somewhere on the stack the value I want to write to. And now what I can do is I can find that some of the data I'm giving it here as a parameter does of course go on the stack. So if I give it AAAA and then some %x's, and notice the last one here is 41, 41, 41, 41. So the fourth word on the stack is the AAAA I put in. So now I can control this number. And therefore I can write to any number, I can write to any address I choose. And to prove it, I can do this. I can use a 1, 2, 3, 4 instead of an AAAA. And then I'll see 1, 2, 3, 4 here, 31, 32, 33, 34, which is the hexadecimal code for the characters 1, 2, 3, 4. So that just proves I now know that the fourth item on the stack is the first 4 bytes I put in. So I can write to an address of my choice. Now, let's talk about how you take over the box with a write operation. When we did a stack buffer overflow, there was a return pointer at the end of the stack frame. And all we had to do was overwrite that, and that would get copied into the instruction pointer and control the box. But how do you take over the box with a write operation? The answer is this. You can use GDB minus Q ED204, and we can disassemble main. All right. And notice what happened here. I'm going to go till I see all the code, press enter a few times. All right. Now you can tell what's going on here. Let's get the source code. Here's the source code. So the source code is if something is true, then print a message and exit. So if you just look at the yellow calls to the C library, you can see here it is printing something and then exiting. So this is the print that will print a message warning you that you had to include a parameter, and there's the exit there. Then you're going to call string copy, that's this command, and then a print, then a put character, which is printing that carriage return, and then an exit. So without reading the rest of the assembly code, you can see how this corresponds to C. All right, now, notice the important thing for us here is to notice that here's the vulnerable print is here. This is where we get a chance to write to memory. And after that, it calls putchar and exit. So what I can do is I can just override the pointer to one of these C library functions. If I can find one of the pointers that controls the exit function, then when it calls exit, I can redirect it to run code of my choice instead of what the developer wanted. And that you can do. That's called the programming linkage table and the global offset table. Those are the names of these things. And you can see them with objdump. Objdump minus R for relocation of this program will show you, here's the C library functions this program uses, printf, string copy, and putchar. Here's exit, the one I wish to hook, and here's the address where it is stored. So it doesn't jump directly to the kernel to run this code. It jumps through 2 layers of indirection, one in the program side and one on the operating system side, because you might want to update your operating system. And if you do that, you don't want to have to recompile the programs. So if the operating system changes the location of some of the methods, it will just have a table of pointers which it updates to point to that, so your previously compiled programs will still run. And the same thing happens on the other side. You might want to update your compiler and recompile a program, and you wouldn't have to change your operating system for that to work. So at both ends, there are indirection pointers, and you can overwrite them. So here's one of them, the global offset table. So this address, which is 804.0804.A014, that address controls where the exit function is. So I can now write to there. I can do it in the debugger. All right, so I can examine it here. I'm going to examine one word of hexadecimal at that location. All right, and now this is the actual address. This 80.04.8366, that's the real address of the real exit function. But I can run the program and I can print this data. And what this is going to do, let me show, this is going to run the program with these command line parameters. And this is 0804A014. It's this address in little endian order, and then %x, 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 %n, because remember the fourth item on the stack is this data. So this will write something into that location. So let's run that. And now I get a segmentation fault. And if I go to look at that location, it now contains 00001B instead of the right value, which starts with 0804. So I did write to that location, and when the program tried to execute the C library function exit, it tried to execute this, tried to go to this location, and that's not valid, so I got a segmentation fault saying you're trying to execute code at this ridiculous low memory value which userland cannot access. So I did succeed now in making an exploit. This is a denial of service attack. I'm now able to make the program crash. All right, and I understand why it's crashing. So the next thing is to gain control of it. All right, and that's what the %n format string, it prints to that location, but what does it print? For some ridiculous reason, what it prints to that location is the total number of characters that have been printed so far, which in this case is something like 12 or 16. You know, what I did was I printed 4 characters here, and then %x, %x, %x. So that's like 4 plus 6, that's like 10. And then percentage, just something like 12 characters have been printed at that point, something like that. And it printed as 1B, so I guess a little bit more than that. But anyway, that's what it does. So you can write 4 bytes. And what you do, I'm going to make a Python code that will write 4 bytes to it. So I'm going to nano f1.py. All right, and so I'm going to print all these things and then format. So I put these 4 patterns on the stack. This is going to be 4 bytes and then 4 bytes of junk, 4 bytes and 4 bytes of junk. So now it's %x, 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 %n. This will write to the first location. Then %x to skip through the junk, and another %n. It'll write to this location, and that location, and that location. So this is going to write 4 times to each of the 4 bytes of the 32-bit word that controls the pointer to the exit function. So I save this, make it executable. All right, and now I can run it in the debugger. All right, so I go back to my GDB, and I run on $./f1.py. That will, this $ parentheses will run that program and take the output of it and put it in my command line here as a parameter. A lot of people like to do this with the backtick character. I find that confusing. I prefer the older system where you use a $ parentheses for it, but it's the same thing. So that will run it. And now, here you see it, junk, 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 junk. There's non-printable characters that were skipped. And then I can now examine the location, this memory location I was writing to. You can see what's in there, and what's in there is 37, 3F, 47, 4F, because I printed all this stuff, which is apparently 37 characters in some part of it. The part of it, when I wrote to the first one, it was 37 characters. Then when I wrote to the next one, it was 3F, 8 more. Then 47 and 4F. So those 4 write operations wrote this value there. Now the value is still a stupid value that does not refer to a valid memory location, so the program still crashes. But now I've seen I can control all 4 bytes. So to target a specific value, this is the code that will do it. And what you do is you have multiples of 256. You carefully write much more. So I'm going to print what you can do is you can put a counter before the number you write in the format string, and that makes it longer. So if I print, let me just bring another text Here, right, so if I print, let's get rid of this. So if I print f %x, and then some variable like I, it'll just print it as long as it has to be, but I can make it %8x. And then it will always be 8 characters long, even if it has to pad it with zeros. And I can even make it really big, like 256x, and then it will always be 256 characters long, a long string of zeros. So you can add integers here, and that's what these W numbers are going to be. So here I write W1, W2, W3, W4, and then the format. And so that will put those numbers before the format string. All right. And see here I make them so that each one of them is a multiple of 256. So it's going to count through a whole byte worth of unsigned integers up to 256 and something higher, so I can control the lower 8 bits of the number and make it anything I would want it to be. So I'm going to try and target this value, AABBCCDD, to show I have control of all 4 bytes. So this is going to be f2.py. All right, so let me get rid of that. All right, and quit out of here. All right, so that's what this is going to do. There's the code. So I'm going to save it, make it executable. All right, and then run it in the debugger again. Yep, and then run, taking data from the second program, f2.py. All right, and now I want to see what I got in that value. I did write all 4 of those bytes, and what did I get? I wanted to get AABBCCDD, but you see, I didn't get that. I got B1. Now, AA to B1 is a distance of 6. It's A, B, C, D, E, F, 0, 1. It's either 6 or 7 away. A0, 6, I think it's 7 away. Okay, so I'm off by 7. Now, this happens a lot. The different systems are a little bit different. So I need to adjust my code to be different by 7. And I think, I'm just trying to get back to my narrow, and I think what I want to do is change this 29 to a 22. I don't remember whether I want to make it bigger or smaller. I remember from last time I've had this problem. I'm going to change this by 7, its hexadecimal number. So if I add 7 to 29, 9 and 7 is 16, so I get 30. I think this has to be 30, is what it has to be in a modern system. So that number depends on the details of how your system is using memory, and it varies a little bit. So I think this is the correction to make it run on this system. I think what's going on is the version of Debian, but I'm not quite sure which aspect of the software is controlling this. But I think that will do it. So now, if I go back into GDB, and I run, taking data from F2, now I can see here AABBCCDD. And if I look at that memory location that used to point to the exit, it now points to AABBCCDD. So now I can control the instruction pointer like we did before. Now, if there was something like a win function here, I was trying to run that the developer had put, I could just put that address in. But here, there is nothing like that. So now we're having to do a more advanced form of exploitation here. We're going to have to make some malware. And that's why I thought you might want to see this. And, again, if this project seems too difficult for you, you can go on to another one. But if you do want to learn how to develop an exploit, you learn a lot about how machines work. So I'm going to make this one with f3.py. And let's talk about it. I get out of here. I make f3.py. All right. And here, I've got this program. Now, I have to remember to make the same correction here. These should all be 30 on my system. The demonstration, when I wrote the project a few years ago, 29 was the right value, but on this modern system, it appears to be 30. All right. And now what I'm going to do is write AABBCCDD, And the only difference here is I'm going to mark making an exploit. And the way you make an exploit is you have a NOP sled, which is just a series of no operations, and the raw binary machine code for no operation is 90. So I put in 100 NOPs. Then I make fake shell code, which is 250 CCs. CC is a break command that will jump back to my debugger. So I've made a fake exploit here where I've got some NOP, 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 and then I've got some break back to the debugger. And then I'm going to write that stuff after I do all the format strings to write to memory. I'm going to just put it on the stack by writing NOP sled and shellcode here. So this is how these exploits work. The developer didn't write some code that I can use. So I'm inserting some strings which will be put on the stack, and then I'm going to run them as code. So that's what I've done here. That's what this is going to do. So make it executable. All right, then go back in the debugger and run, taking data from F3. All right, and now I can examine this location, and I see again I've written an AABBCCDD, and I need to figure out what value to write there. And the way to find it is to look at the stack now. If I do X, 100 words of hexadecimal, ESP, I'll see what's on the stack. And if I go up here, here's some random stuff on the stack. Here's my 90s. These are my NOPs. Here's my Cs. Those are my breaks where I'm going to put shellcode. So all I do is now I know where the data I fed in went. And I can now find an address. So I just pick an area in the middle of my NOP sled, like here, and I copy that value. I want to jump to that address. That's where the code I injected went. I injected raw machine code, and I can run it by jumping to that address. And as long as I'm somewhere in the NOP sled, it will just execute the NOPs, NOP, 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 because NOP does nothing, and get down to the breaks. So now I have that address, which is what I wanted. All right, and so now I'm going to copy f3.py to f4.py and nano f4. All right, and in here, I'm going to put in that address I copied there. And so that's what I want to put in instead of this AABBCCDD stuff. I want to put in FF, CF, and 5C. I hope I've got those right. I think I got to put them in the other order. I think byte one, no, it got to be other order. Okay, backwards. 5C, CF, FF, FF. There, I think that'll do it. That will now jump to my NOP sled, and all the rest of this should be fine. So, right, I do need to Chmod, yeah. Okay, and then I do GDB minus, just go up here. All right, and now I run, taking my input from f4.py. Okay, and now I'm going to do, how did I want to do this? I think I just want to examine the stack. Yep, X, 100X, ESP. All right, and now the point is, it crashed at this location, CF95. That's where it was when it stopped. And so I can see CF95. This is HC, this is 90, this is CF95 right there. So it worked. I jumped into the NOPs, it executed NOP, 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 and it stopped as soon as it hit the first CC. So this means I now control this box. I can now execute code of my choice. I inserted some code and I was able to execute it. So I found a good address, and this machine does not have stack protection turned on that prevents you from executing code on the stack, which is a common defense these days. So Now all I have to do is find real shellcode to run here that will do something useful instead of just breaking back to the debugger. And for that, you use Metasploit. Now, here I have some steps where you test to see what characters are bad, but it turns out that they're all pretty obvious. When I'm inputting a command line parameter in a line of bash, like I did here, let me get out of here and show you that. All right, if I run this program, ed204, it'll tell me I need a string. So if I put in a string like hello, it'll take it. But if I put in hello space there, it only gets, it knows the third parameter, it won't run. So I can't have a space. If I have a space, it'll interpret this as two parameters. And the same thing's true of a null byte or a tab or a carriage return or a line feed. So it's pretty obvious that these are the null characters. And there's a way to go and prove that by trying all characters. But it's pretty obvious in retrospect that those characters are forbidden. So what I did was I used Metasploit, which is a tool that writes malware. And here you can define malware. What this is going to do is make a Linux shell, which gives you remote control over the internet of the box. It's going to avoid these bad characters. And this prepend fork equals true. I'm not really quite sure what that is. I put that in because it makes it more reliable. And then I want the output in Python. So this is going to write Python code for me that will do that attack. So I clear. That's what Metasploit does. I don't have MSF Venom. Okay, I need to install Metasploit on this box. So let me do that. That was right at the top. I thought it had already been done, but it's not hard to do. You curl the installer from Metasploit and put it in a program called MSF install, or in a file. So this will just download a script that runs it. And now I think you just chmod and run that script. Yep, chmod 755 MSF install and sudo /MSF install. All right, that will do it. Install Metasploit on here, which is a famous hacking tool that you use to write malware, among other things. And by the way, of course, this is relatively harmless malware because since it's public knowledge, all the antiviruses know about it. But it's a good teaching tool. All right, and then I'll use MSF Venom, which is the command in the Metasploit package that writes standalone malware. It can do other things too. It can do interactive things, like attack a whole fleet of computers and gather all the responses and so on, fill them in a database and so on. It can do a lot of fancy things. But here we're just doing a simple thing. We're making a single piece of standalone malware, and I'm going to say no for this question. Ask me about that database in case I'm doing a corporate pen test and I want to hack 100 machines. That's not what I'm doing. So there, we have malware. This is the Python code that will generate the malware, and it's only going to need 133 bytes to run. But there's a problem. If you look at this malware, before I was able to find a null byte in it. Oh, that's right. Now I told it to avoid null bytes, so it should be all right. So that should be my Python code ready to go. Okay. So I can just, after I've got my malware, I did already got bad characters. I skipped over that part. There's my shellcode. Okay, right. So now I copy F4 to F5. By the way, I'll mention this is a really good practice whenever you're developing anything like this. Have a whole series of files. Don't keep editing the same file because very often you make a mistake and you say, gee, I'm on the wrong track. I wish I could go back to the thing that worked a couple times ago. So I always make a new file, a whole series of them when I'm developing anything like this. So now in here I had my shellcode, and I'm going to paste in that stuff I copied there. There's that thing called buff. I'm going to use that instead of the shellcode. And so I'm not going to use the shellcode anymore. All right, there's my buff. So I want to print buff here instead of shellcode. And that's probably all I have to do. But I'm going to add padding. Okay, that's what I wondered. It's a good practice to always make your exploit the same length all the time. So to do that, I'm going to put in padding. which is a byte stream of A times 250 is the total length minus the length of shellcode, of buff. I think that'll do it. Yeah, that'll put in enough A's to make the total length 250. And so now, before it ran through the NOP sled, NOP, and then it stopped because I had nothing but CCs here. Now it's going to run through the NOP sled and then execute this shellcode that came from that malware engine. So it should give me control of the box. So I should be able to just, okay, we'll run it in the debugger. All right. Probably could run it outside the debugger now, but that's all right. I'll stick to my plan here. There, I debug it. And I'm going to put a breakpoint. Let's do disassemble main. So we can see, now remember we looked at this program before. This is the help message. This is the string copy. This is the print that does the vulnerability. And then exit here is where it's going to call the exit function where I modified it. So I want to go after this command. I would like to put a breakpoint here, which is main plus 115. I'll put a breakpoint there, and I'll be able to examine the state of memory after the exploit has run, but before the program tries to execute it. So I'll put a break, star main plus 115. All right, and now I run, taking the input from F5 .py. All right, now it hits the breakpoint. Now I can examine the address that I've written into the pointer that goes to the exit function, and there it is, FFFFCF5C, and now I can examine the stack. All right, so this was CF5C, and so here's CF5C, so the address that I put in there was something like this. So it's in the NOP sled. That's good. So now it's going to run NOP, and then this stuff is no longer just a bunch of CCs. This is the code generated by Metasploit, and these 41s are the padding I put in at the end. So here's all the data I put on the stack. It's going to run this. It's going to run that shellcode. So if I just continue, should be the next thing that happens here. Yep, continue. Oops, first I have to finish this by pressing enter. Okay, now I can continue. All right, and now it forks and exits normally. It doesn't crash. And so if I quit here and then do sudo ss -pant, I think I can even do pant l, I'll see there's a process listening on port 4444, which is the default. So that's giving me control of the box. And you can control the box by connecting to that with Netcat. This is listening on port 4444, and anybody that connects to that port will be able to control the box. So I can, for example, take it over from my Mac here. If I just open another terminal, which should be somewhere. Hello? Up here? I'm not seeing it. How about Control N? Will that open another terminal? Windows N did, all right? There's probably another terminal hiding here somewhere. But anyway, here's another terminal. So if I get the IP address of this box, which is 192.168.0.24, I should be able to do a connection with Netcat. 192.168.0.24 on port 4444. Yep, I'm in. I can now do ID and LS and who am I and date. You know, I'm now into the box. I now have remote control of the box by connecting on that port. That's what a listening shell is. It starts a listening process, and anybody that connects, it lets you control the box at the command line. Now, the way to end this, by the way, the logic is to just exit here with Control C. And when you do that, if the client disconnects, then the server will disconnect normally. And now if you do this SS -pantel again, you'll see I'm no longer listening. If you just kill it, the server, and don't turn off the client, then you'll get a hung process that will tie up that port 4444 for like 2 or 3 minutes. It's very annoying when you're developing exploits. Anyway, so that's what I wanted to show you. you get to see a few steps of a real takeover there, and you'll learn a bit about how indirection of C library functions works. So let me stop this.